the audience. And I said, yes, sir. And the young lady said, excuse me. So I've had this experience before, thank you. I'll remember that. And I hope it wasn't you.
No, I wasn't there.
But we appreciate your patience in giving us an opportunity to get all this set up. It's been a hectic schedule. First of all, I would like to welcome all of you to this Tesla Coil workshop, sponsored by the International Tesla Society and its 5th biannual symposium. It's wonderful to see this much of a turnout for this kind of an event. And before I tell you what the itinerary is going to be of our event, first I would like to introduce the people who have made this possible, the people who have been assisting me through thick and thin and who have been instrumental in bringing all of this equipment before you. Beginning with Mr. Lowell Beasley on the left, and my young son, the first harmonic, as we call it in the ham radio industry, Mr. Brent Turner, and Mr. Pete Miller. And of course, my name is Bill Wysock. We come from Los Angeles, and as you know, Los Angeles is famous for a lot of things these days. It's famous for riots, it's famous for earthquakes, and I think I'd rather move here than go back there any day of the week. But that notwithstanding, we are going to have to go back. What we're going to present for you here today is a Tesla Coil workshop. The slated time for this workshop runs from 1 p.m. to 4 p.m. Now, many of you have probably attended seminars such as Hewlett-Packard or Tektronix and this sort of thing. We're going to try and pattern this event similar to that type of an event, which means we will go through 4 segments. The first 2 segments are going to be slideshow segments where I will provide an oratory and we'll have just visual graphics. We'll bring the house lights down nice and low, so hopefully you'll all be able to get a good vantage point. I think you'll find the slides rather interesting. We'll take a short 10-minute break after this first carousel is finished. There's 80 slides there. It'll probably run about 45-50 minutes. Following that 10-minute recess, we'll reconvene. We'll go through the second series of slides, which goes into depth into spark gap technology specifically. And all of the elements that we're going to talk about are grassroots elements. These are elements that make a Tesla coil work better or worse or not at all or fantastic. We're going to go very light on theory as far as long hair theory, quote unquote. We're not going to get involved in any deep mathematical formulas or analysis. There's plenty of material available for that. What we would rather present to you here is an opportunity to understand the finer points of building a Tesla coil, tuning a Tesla coil, and operating a Tesla coil safely, and how you can choose and select from a variety of different components depending on the size of coil and the design of coil you want to build. So you should go away from here with maybe a little bit more information that you've already had to experience. I would like to again thank the International Tesla Society for this opportunity, and I'm going to talk about another organization, which is the Tesla Coil Builders Association. Do we have any TCBA members here in the audience? Quite a few, all right?
All right.
For those of you who are not aware of what TCBA is, I will be talking about that at the close of the program, which will also be a question and answer session. So we have our first segment is slides, a break. Our second segment will also be slides on spark gap design. Our third segment will be demonstration of small apparatus here in front of you, and we will correlate the operation of this apparatus to the slideshow presentations. And finally, we'll culminate with this coil over here to my left, and I will describe its operation and why it is significant being built the way it is. So, if we may proceed at this time, we've got about 12 minutes after the hour. We'll try and wrap this portion up by 2 p.m. so then we can take our first break. So at this time, if we may turn the house lights all the way down, I'm going to simply stand aside. Now, can you all hear me okay?
He wants you to stand on the other side.
He wants me to stand on the other side. Okay, I can do that. Is that okay now? Okay. Can you all hear me okay?
Yes.
All right, very good. Can we bring the house lights down, please? All right, now let's see. Can we also do that? There we go. How many people in the audience recognize this picture? I see 2, 3, 4 hands. This coil is significant in many, many ways for many, many people. For me personally, this coil is significant because this is what got me started in Tesla coils in 1958. This is the coil that I saw as a young child, half asleep, late at night, at the Griffith Park Observatory and Hall of Science in the hills above Hollywood. This coil is significant in Tesla coil history because it was built by Earl L. Ovington, a technician who worked exclusively building high-frequency apparatus for Dr. Frederick Finch Strong. Dr. Strong was an eminent medical practitioner in the 20s and in the 30s, and he was very much involved with electrotherapeutic medicine, specifically radiofrequency electrotherapeutic medicine. And the instruments that he had Earl L. Ovington build for him were used for lectures and for demonstrations as well as for practical medical applications such as diathermy and electrocardiography. This particular coil is one of two coils built exactly the same, the other being in storage in the basement of the museum at the Griffith Park Observatory. You can see a conical shaped secondary coil. It's had the topmost few turns replaced with a different color wire. And the coil form is approximately 3 feet in diameter at the base, 18 inches in diameter at the top, and about 48 inches tall. The ball on top is a 12-inch copper ball. And as you can see, this Tesla coil is placed in an alcove, which is one of the spaces in the west wing of the Hall of Science. The corona tips that you see, the two rods sticking out either side, a means of concentrating the corona discharge or the high voltage spark, and as you can see there are several discharges attaching to the wall in the characteristically Tesla coil fashion. Having seen this coil in 1958 inspired me to find out what is a Tesla coil, how can I build one, I want to have something like that. It really turned me on. Of course, in 1958 as a young kid there was no information available, not that I could have access to. Eventually I found a schematic and I tried to build a coil that looked like this that was tabletop size. And needless to say, it did not work at all. This coil has been at the observatory since 1934 when it was donated by Dr. Strong to the observatory and has been on permanent display ever since, and it is there to this day. And it has served as an inspiration for many people who wanted to build a Tesla coil and maybe never even knew what a Tesla coil was before. The coil that you saw up here in front that is now immediately to my right that I mentioned, you will notice has a lot of similarities to the coil in this picture with the sole exception that this is a cylindrical secondary coil instead of a helical, or that is a conical coil. This thing going to work? Yeah, now we're working forwards. And everything is backwards. Wonderful. This is selection of materials. I understand that the slides are supposed to go inside or upside down and backwards, but apparently this projector works differently. What we're going to start off with here is selection of materials. When you build a Tesla coil, you need to decide what size spark you want to make. And I always ask people when they say they're having trouble with the coil, I say, how big of a spark do you want to make? Stop and think for a minute. If you're going to build a race car, it doesn't matter if it's going to be blown alcohol or top fuel. You need to decide what category you're going to operate in and what your objective is as far as low elapsed time and top speed. I use that as an analogy for Tesla coils because spark length and power and that sort of thing translates into the kind of equipment that you're going to use. So if you're looking to build a coil that makes a 4-inch spark, you don't need a 10,000 watt transformer. By the same notion, if you want to make a coil that makes a 5-foot spark, you really need something that is stronger than a 15,000 volt 30 milliamp neon sign transformer. It goes hand in hand. So when you choose materials, you have to choose wisely. And fortunately for us today, there are a broad range of materials available. First of all, you're going to decide what kind of wire you're going to use for your Tesla transformer or resonator. Shown here in this photograph represents a little bit of a selection of different kinds of wire. This focus adjustment doesn't work too well, Jim. If you can manually take care of the focus, I guess that's about as good as it's going to get. A roll of copper tubing on the left-hand side of the screen works very well. Copper tubing is readily available from hardware stores in a variety of sizes, 1/4 inch, 1/8 inch, 3/8, 1/2 inch, 5/8, 1 inch, and so on. And many coil builders have very successfully used copper tubing. This is also known as refrigeration tubing for primaries of their coils. The spools of wire here are different colors, and I'm sorry the photograph isn't a little bit better, but it represents various forms of what's called magnet wire. Now in the old days, and I refer to the old days as anything before 1960, okay? The old days, it used to be known as form-var wire. Many of you have heard that term perhaps and not understood what it meant. Today, they call it hyperpolythermally enamel wire, or they also call it just straight magnet wire. It is an enamel insulation that is baked on. It typically has a dielectric strength, that is a breakdown insulation strength of about 1,000 volts per mil or greater. It's very suitable wire and a very good choice for small secondary coils up to medium-sized secondary coils. What do I mean by a medium-sized secondary coil? Anything that's up to about 6 inches in diameter and anything that's up to about 3 feet in height. If you want to go bigger than that, I strongly recommend the use of stranded wire and not using this kind of wire, and we'll explain the reason for that in a little bit. This represents a choice of different coil forms. Many people have used sonotubes, which are the kinds of cardboard tubes that are used in general construction and also used for things like carpet rolls from carpet manufacturers. These rolls can be used very successfully if they're properly treated. To use a cardboard roll or tube for a secondary coil form without first treating it is tantamount to disaster if you're going to make any size of sparks of any power. The reason being is that the cardboard absorbs moisture, and what you really need to do is to bake it dry, sort of like a kiln drying process. If it's small enough that you can stick it in the oven in your kitchen without getting your wife or girlfriend mad at you, that's what you need to do. You dry it out. Then get yourself some varnish. The varnish that I recommend and works very well and has for time immemorial, since Tesla coils have been being built back into the teens, is what is called 3-pound cut clear shellac. It absorbs, it soaks right into the cardboard just like water goes into a dry sponge, and it will seal that material. Once you have a secondary coil form that's properly sealed, then you're ready to wind your winding. What is shown here is not a cardboard tube, but various sizes of acrylic tubing, available from a variety of manufactured houses. One thing you need to watch out for so that you don't spend a lot of money, you want to find an extruded tube as opposed to a cast tube. The difference between extruded tubing and cast tubing is very significant in terms of cost. And the tube on the right here is approximately 12 inches in diameter, 36 inches tall, maybe a little bit taller, and the wall thickness of that tube is about 3/16 of an inch. These tubes work very well for any frequency of coil up to about 1 megahertz. If you're going to go higher in frequency than 1 megahertz, if you know that you want to run a small tabletop coil that's going to run high frequency, then another type of material is much more preferable. Here's the sonotube that I was talking about. Many of you will recognize this. And as you can see, the difference in color between the inside and the outside, it looks more brown on the outside, the inside looks more tan. The outside here has received a single coat of shellac and has been allowed to dry after being heated in a dry environment. This picture here represents the application of varnish on a winding. You'll notice, and again, I apologize for all of these slides being backwards. We'll make sure that the second set are put in correctly during the break. The bottle on the right there is what is called Ziegrung. It's a brand of 3-pound cut clear shellac. Now, in view of using shellac, you can also use polyurethane varnishes. The problem with them is that sometimes if they're not carefully thinned down and applied in thin coats, you may not come out with a very smooth finish of insulation for your secondary coil. When you have your secondary coil wound, you want to be able to use a brush that is very clean. If you can develop sort of like a clean room, dry environment, that is very important so that you get a smooth, even coating. And you need to have the patience to put on many coats. In cases of large coils, you would expect to spend up to maybe a couple of weeks putting on different coats of varnish. And incidentally, with larger type secondary coils, you might consider something like the red enamel blipped varnish, which is used in transformer manufacturing. When you have decided what size secondary coil you want, you can then work backwards. First of all, you know what size spark you want, then you know how big of a secondary coil to build, and you'll find out more about how that works when we get into the other part of the theory. The next thing that you're going to need to know is capacitor size. Now, in surplus markets, these types of capacitors are readily available, and they're fairly inexpensive. They're called glass mic capacitors. Most of these are made by companies like Plastic Capacitors Incorporated. You can still buy them brand new. You can often find them surplus. They typically are a mylar film capacitor in a glass shell with a form of oil like transformer oil. The capacitor here on the right, which is much larger, is a GE capacitor, and that is different from the two that are on the left insofar as the type of oil that it uses. This is a pyranol capacitor that is on the right. And because these are glass enclosed cylinders, should there be a dielectric breakdown of one of these capacitors in your Tesla coil circuit, it could actually start a combustion process that builds up extreme pressure, and then you've got a grenade on your hands. Either the glass will crack or the thing will explode. The two capacitors on the left have relatively thin glass shells, and if there's any problem of breakdown of those capacitors, the glass simply fractures and the oil starts to leak out. It's a fairly benign thing when they break down. The capacitor on the right, watch out for that. That's about 0.012 microfarad at 25 kV DC. That's the rating on it. You may run into some of these. Watch out if you use them, because if they start to break down internally, you can go away and 10 minutes later there's still a chemical chain reaction process going on, and it's building up pressure, and the glass on that capacitor on the right is approximately 3/8 of an inch thick. Now, how much pressure do you think it would take to explode a glass vessel 3/8 of an inch thick? Hundreds of psi. And when it goes off just like a grenade. I'm telling you this from experience. I had one of these explode on me in 1975 in my living room on a coil that I had built, and I thought I was saving myself money by finding these surplus. I counted my lucky stars that I was the lucky recipient of having these wonderful, great capacitors. Nice size, nice capacity, beautiful shape like brand new. And after firing a small tabletop coil producing about a 2-foot spark with an input power of about 1.5 kilowatts, my guests who I had been entertained walked out the front door, kaboom! It literally ripped the base unit where the primary coil was apart. It tore a hole in a 20-inch diameter aluminum toroid. That's the same amount of force as if I'd probably shot it with a .22 caliber bullet. So watch out for these things because they can be very dangerous. Other forms of capacitors that are much more preferable to use, if you can find them surplus or if you have to buy them new, you're going to spend money through the nose. In the background, a tall capacitor, that one happens to be made by a company called Tob Deutschmann. That is a capacitor very similar to what I'm using right now for this display that's up at the high school. It is about 0.025 microfarad at about 40 kV. It also is a mylar film wrapped capacitor, and there are actually sections of mylar film and foil inside. And of course, again, oil insulated. Being a metal can, should there be a problem with breakdown in that, the can will simply start to grow out. So it's a safe unit to use with that respect. You need to check the oil to make sure that it's non-PCB. We'll get into what PCB means in a minute or two. The capacitor on the right in the background, also black, that's a GE power factor correction capacitor. You look at the label in the surplus house, it says 0.125 microfarad, 40 kV, and you think, wow, that's perfect for my big coil. Wrong. The reason why is because that kind of a capacitor is used only for AC power factor correction in power lines, and it uses a paper dielectric, not even a mylar film. You need capacitors that are mylar film, polypropylene film, polyethylene film if you can find such an animal, or mica, all very desirable. But you need to stay away from paper-based dielectric capacitors, and you have to educate your eyes when you look at these things to see what the difference is, because oftentimes you can buy a capacitor and think, oh, this is great, and then you take it home and you hook it up in your circuit, you find out, gee, my Tesla coil doesn't oscillate. What's wrong here? The capacitor's not shorted, it just won't oscillate. it's too high of reactance. And it's because of this paper dielectric. And then you have to go back to the source and say, hey, I want my money back. I can't use this capacitor. They say, hey, this is a component. How do I know you haven't destroyed it? You bought it. It's yours. In the front here, you see mica transmitting capacitors in a variety of sizes, from the left going to the right. The one on the extreme left there is made by Aerovox. It is a very good capacitor if you can find it. That runs about 25,000 volts and about 0.015 microfarad. A beautiful building block for almost any size of coil. Will handle a great deal of power as far as input current, but will not tolerate overvoltage. And in a Tesla coil that's spark gap driven, there's a phenomenon called resonant rise, which we will talk about. And that means that even though you know that the applied voltage at 60 cycles from your transformer is, say, no more than 10,000 or 12,000 or 15,000 volts at most, when you have resonant rise, you may exceed that factor by more than 2. So if you've got 15,000 volts under load going into your resonant tank circuit, your capacitor circuit, you may find that you have in excess of 30,000 volts or more. So you have to be careful about these capacitors, and the way to do that is to protect them with safety gaps, which we will talk about. Capacitor to the right, just next to it there, is a Coronel doublier. Very famous maker, and capacitors made clear back into the 20s. Again, an excellent choice. These are smaller Coronel doublier capacitors in the middle and to the right. The Coke can there is there for only size comparison. On the extreme right is again a plastic capacitors incorporated capacitor. Very usable for small power, but watch out. Even though it's the right kind of dielectric, it's in the right kind of an enclosure, it's got the right working voltage and so forth, you have to be careful if you're going to build a big coil and you're going to put a lot of power into it, and you've only got this small capacitor that fits in the palm of your hand, and you're going to try and cram all that power into that small capacitor, it's going to heat up on you real fast, regardless of what the dielectric loss tangent is of the dielectric of the capacitor. The amount of surface area of a capacitor has to be considered as one of the primary factors when you decide what power level of Tesla coil you're going to build and operate. Transformers. Transformers are every Tesla coil builder's bane. Why do I say that? How many people here have burned out a neon sign transformer building a Tesla coil? Yeah. And it's a constant debate as to how you manage to make a neon sign transformer survive. Sometimes you run across a real gem. Maybe you've got a 15 kV transformer at 120 milliamps and you think, boy, I'm going to use this forever. I'm going to take care of it. I'm going to cherish it. It's going to work beautifully. Next thing you know, it went poof. We'll talk about how you can get around that very simply and very effectively. Better transformers are needed for higher power coils. Rules of thumb. If you're going to build a tabletop coil, like I say, anything up to like a 2-foot spark, neon sign transformers are great sources for power sources. They need to be modified and treated very carefully in order to be used successfully year after year after year. If you do the right steps, and we'll show you what that means later on, you will have a very successful unit. If you want to build a coil that makes a 3-foot or larger spark, it's time to consider a different kind of transformer. Many of you have probably seen articles or know people who have worked with coils where they start paralleling neon sign transformers. Well, I've got 5 units here, they're 15 kV and they're 60 milliamps apiece. I put 5 of them in parallel, by golly, I've got 300 milliamps. Yes, you have. But unless you modify the internal current limiting shunts, which are part of the magnetic core, as the current rises, the voltage drops. So as far as each transformer is concerned, if they're all phased correctly, yeah, you might have 300 milliamps across a direct short. But that's all the more current you're going to get. And where's your 15,000 volts? It's gone. Because it is what is called a saturable core transformer. You need to consider the use of a non-saturable core transformer, which is different insofar as there is no internal current limiting in the transformer itself. Plate transformers, the one that is shown here on the left, is a good choice if you can find a transformer that is well built. They're getting harder to find. The one on the right in the big black case, a real gem, and it weighs just about a ton, so to speak. taps from 0 up to about 150 volts, center tap on the middle insulator on the right, and the 2 end windings of the secondary on the end feed-throughs. That transformer there is about 1.5 kVA rated. You could probably get up to about 3 kVA out of it for a short period of time before you go to complete core saturation. That transformer there on the right is only good for about 6,000 volts, and the largest plate transformer that's tabletop size that you can just barely carry around like this that I've ever seen was up around 75 or 7,600 volts. When you consider the construction of any Tesla coil that's spark gap driven, whether it be for tabletop size or larger, try and keep yourself in the range of at least 10,000 volts nameplate rating. And anything up to and including 25,000 volts is excellent. If you're going to build a super coil, then it's time to consider voltages above 25 kV. Here's a transformer that is a real choice. 50 kVA, that is 50,000 watt transformer. And a gentleman about my size standing next to it for comparison. Commonly referred to as pole pigs. If you find these, they're excellent to use. It's worthwhile making sure that they are not PCB contaminated. PCBs, I keep mentioning PCBs, polychlorinated biphenyls. It's a form of contamination which, when oxidized through a burning process, is carcinogenous. But in an inert state, I personally believe that it's relatively benign. Now, power sources.
This is your backyard, Michael.
Yeah, this is my backyard. You need to make sure that you have an adequate power source when you build a Tesla coil. If you're building a tabletop coil, not a problem. If you're building a bigger coil, you need to consider your source of power, because if you have too much drop of current in your line getting to where your Tesla coil is, you're fooling yourself as far as tuning. Insulators. Insulators can be done all different ways. And you will see some insulators here in some of this construction that really shows some innovation. You can use PVC piping, for example, very effectively. These insulators here run the gamut. In the front, from small steep type, which is a type of porcelain that's very high dielectric strength and very low dielectric loss tangent. These are terms which, if you need explanation, we'll get into after the show, and we'll go to the question and answer period. In the background, you see utility pole type insulators. Sometimes very expensive, but very worthwhile if you can get them. Discharge electrodes. Spheres work very well. Most commercial supply houses can supply hollow copper spheres. These are copper spheres that have been brush polished, and they range in size from the lower part of 1.5 inches up to 8 inches in the upper left. Now this picture is a little bit washed out, I'm sorry, but that young lady standing there is standing next to a toroid, which, as you have seen already, is the discharge electrode of choice for most medium to large power Tesla coils. That toroid is 8 feet across and about 20 inches in cross section. And it's made out of aluminum tubing with girders all the way around to support it, rather than being a completely spun aluminum torus. Spark gaps. We're talking about the basic components of your Tesla coil. What are you going to do about a spark gap? You can find commercial gaps eventually if you dig hard enough. Most of the old electromedical machines, diathermy machines, have spark gaps very similar to this right here. Tungsten faced. Very worthwhile material to use. If you can't afford that, there are other materials which we can suggest. You can use carbide, tungsten carbide, readily available from tooling supplies. You need a hard material rather than a soft material, because the spark does not want to deface the surface of the electrodes. Sphere gaps. Sphere gaps are good for what? They're good for overvoltage protection as a brute crowbar type of device. Again, you can combine components that you find surplus and use these types of ball gaps to act as a sort of a crowbar so that you don't overvoltage your circuit. What about a rotary gap? A little bit more sophisticated than a standard spark gap. This is a commercial unit running at 1800 RPM, and in the second part of our presentation we will talk about why that is significant. Rotary gaps are of two forms, synchronous and non-synchronous, and we'll talk about that further. Another form of spark gap, a quench gap, that is a series of parallel plates stacked together with a confined airspace between them. And what quenching means, we'll talk about that further. So when you choose the type of spark gap that you're going to use, that has everything to do with the success of your Tesla coil, assuming that you're building a spark gap driven Tesla coil. This is a quench gap assembly right here. Those are stainless steel plates and phenolic spacers in between. And we'll show you further on the nature of the sparking surfaces. Here is a form of a rotary gap. Now in the wireless magazines, this was often referred to as a Marconi style rotary spark gap. It just so happens that somehow he managed to get credit for this design of rotary gap instead of Tesla, but that's another story in and of itself. Here the disc is about 8 inches in diameter. The motor started out at 1725 RPM. The armature has been ground into 4 flats to make it salient pole or dominant pole synchronous at 1800 RPM. We will explain in the second part of our presentation why a synchronous rotary gap is very much advantageous over a non-synchronous gap. You'll notice that there's 12 electrodes there around the periphery of the disc, plus 2 sets of upper and lower stationary electrodes, so it actually forms a double rotary gap this way. Here's a coil form being readied on a workbench, again a can of Coke in the background. This happens to be a piece of sonotube, and the bottom base there is a piece of wafer board, and on top here is one of these toroids that we talk about, hollow spun aluminum, available from a variety of sources, and fortunately these days not terribly expensive. If you're going to follow what Tesla did and do something of a classical nature, you might want to use a mechanical interrupter or a mercury interrupter. This is a diagram of one of Tesla's very successful high-speed mercury interrupters. You ought to have access to a machine shop if you want to build this type of device, or else have a friend who is a machinist who knows how to say nothing but, "Yes, I can." Here is one of Tesla's original transformers with a mercury interrupter attached to it. That is the process for converting low frequency to high frequency, is with that interrupter. Great for tabletop coils, but you don't want to use it for high power. The difference about types of interrupters, whether it be vacuum tubes, mercury brakes, rotary gaps, quench gaps, it all has to do with efficiency. And we'll discuss that further. The one thing you want to do, even if you want to build a vacuum tube Tesla coil, is you want to be careful about your design parameters. Notice how tall the secondary is. It's about 3 feet tall. It's 1.5 inches in diameter. I want to see anybody raise their hand who thinks that coil could work very well. Good, good, I'm glad to see that. Yet at the same time, remember I talked about at very high frequencies using materials other than like Lexan or lucite or sonotube. This is an actual radio frequency pulse transformer. Down at the bottom are 2 turns, and that's Teflon on the white material. And you'll notice that it's actually an air core on the secondary, and it just has ribs supporting the helical winding of the secondary. That thing is about 10 inches tall, and it's designed to run at something like 20 megahertz. And it produces an incredible torch flame, but the input power is about 5 kilowatts. Here's an example of a Tesla coil being built, showing a number of parameters. The secondary, the 20-inch discharge electrode, the secondary is about 5 inches in diameter. It has a lucite sleeve over the outside of the secondary for additional insulation. Notice that it has a helical primary. The person who built this coil couldn't afford expensive materials, so he took plywood and wood dowels and formed a cage upon which to wind his 1/4-inch copper tubing. Underneath you see a quench spark gap, capacitor bank, and filters. The 2 mica capacitors and the 2 red cylinders at the right on the base form an LC filter for the input of the circuit. Here's an example of a variety of different types of Tesla coils. The one just to the right standing about 7 feet tall with a 30-inch toroid on top. The one in the middle standing about 4 feet tall, and the rest are a little bit too dark to see in this particular picture. But that's a collection of about 5 different sizes of Tesla coils, ranging from large laboratory type apparatus down to tabletop size. Incidentally, the coil that's the tallest one here, if any of you know Dave Archer, who is the person who does electric painting on glass with a Tesla coil, that is the coil that was built for him. Here is the base of this coil right here. Now this picture was taken in 1975, and this coil is here at the symposium for two reasons. Number one, to demonstrate and make sparks, and number two, to give credit to its builder, Richard Gibson Arant. Those of you who are members of TCBA probably recognize the name Dick Arant. This was Dick's coil that he built as an inspiration after he first got interested in Tesla coils from the Griffith Park Observatory. It has many similarities in design characteristics as compared to that coil. Notice the primary is aluminum, flat aluminum strip, but not one, but 4 strips run together to add bulk to it and increase the amount of cross-section. Well, I keep coming back to power. The problem about Tesla coils and Tesla coil builders is that they're never satisfied. They always want to go bigger and hotter. And those of us in the industry, and those of us who've been around it for a while, and paid our dues burning up transformers and capacitors and getting the neighbors ready to shoot us, we have a motto, which is TFMS, Tune for Maximum Smoke. Here is a discharge off of a coil that was shown in the previous picture. What's interesting about this is that the coil form is only 24 inches tall. The longest corona discharge coming off of that is over 45 inches. And yet there's no insulation down inside the center of the tube. And the input power here is only about 1.5 kilowatts, 1,500 watts off of a 120 volt circuit. And it's driven with a quench spark gap and 2.04 microfarad capacitors. And this is a time exposure in a dark room of about 1.5 seconds. Notice the breakdown between the primary and the secondary. This is what Tesla talks about in his Colorado Springs notes and in his patents. And that discharge, and you can see the snaking here, that's really very interesting as it goes up the side of the tube. The hot spots right here, and there's the primary, and there's the breakdown. That's what's called a D'Arsenval type breakdown. And that's only because the literature has differentiated between Tesla discharges and D'Arsenval discharges as the amount of current available. Now in this picture, the person in the lower center, that's Dick Arant. And the person in the upper left here, that's Jim Schaefer, a friend of mine. He's standing on an insulated spool and he's taking the discharge off of that coil you saw in the previous picture. When you take the discharge off of a coil, be very careful. If you don't know what you're doing, don't do it, because people have been killed. How many people know Henry L. Transtrom? He wrote a book on Tesla coil theory, design, and construction. He was killed during one of his own demonstrations. And this was a guy who had been around the field for many years. Here's a picture of this coil that you see just to my right, discharging in my front yard. Notice the amount of corona coming off of this flat plate, which is right here. And notice how it curves down in a semi-arc. It's following electromagnetic lines of force set up around the secondary coil. When you do photographic studies and try to understand how the magnetic fields are set up of coils, you can actually use the corona spray to indicate what the field intensity is and how it's distributed. Notice also that the corona coming off of the two metal points here. Here's a closer up view of that. Again, notice the corona coming off the flat plate and the corona coming off of the 2 points. This is very interesting because what you start to do when you work with medium and higher power apparatus is that you can start learning a great deal about the mechanisms of spark breakdown at high frequency and their various characteristics. Now here is that same coil. This is about a 2-second time exposure, and it's operating at full power, 3 kilowatts. And on the left-hand side here, you see a small metal rod that's grounded. That gap is about 5 feet across. Notice the amount of corona leakage coming off the top plate. You see all that? That's wasted power. Dick designed it this way because in the day that he built this coil, which was back in 1952, that's how you built coils. Now notice what we've done here. We've taken off this ball and this corona point. We've put on a 20-inch toroid with a small tack sticking out the side. See the faint glow around that disc, this disc right here? You can barely make out that glow, but if you look at it, it's not going straight out, it's bent down slightly on a curve, like an inverted cone. Look at the amount of spark display coming out of it. We've done nothing else to the input power or the tuning. We simply changed the terminal capacitance. That's why when you build a Tesla coil, your size and source and shape of your discharge electrode is extremely important, right along with your spark gap and the other choice of materials that you have. This shows you another view, and let's see, what do we have? We've got something, we've got the gentleman who's, there you go. Now, you can see the corona spray. See how it bends down slightly? It's being bent down by a process of electrostatic deflection, not from the secondary coil itself, but from the field that's set up around the toroid. So if you want to really get into Tesla coil esoterics, build a Van de Graaff generator and experiment with electrostatics and learn all about how E fields are distributed. Here's a single pulse off of that coil, but what's that on the left? That's a resonant receiving coil that's simply grounded. This is a little bit longer of a pulse. We still have the 20-inch toroid on the coil. The coil on the left there, about 7 feet tall, 20-gauge wire, 9-inch diameter, fiberglass form, 8-inch copper ball on top. It's simply connected to the same ground that the input of the coil is connected to. The gap across there about 6.5, 7 feet. Look at this. Now see the corona coming off the ball on the left there. That's about 2 feet long. That's resonant rise in the ground circuit, as opposed to electromagnetic induction. That second coil is too far away to be in the primary field radiating from this coil. So how is it being excited? Well, first of all, it's on a harmonic of the fundamental frequency of the coil, the driving coil on the right. Secondly, it's connected to the same ground. So it shows that Tesla was right about talking about pumping electricity in and out of the ground. You have to change your thinking about what is ground when it comes to RF at medium or high power. These discharges are about 7 feet across. And what is remarkable about this is that if you look at Colorado Springs notes and the pictures that Tesla shows of the laboratory of the unconnected coil 22 feet away, you start seeing many similarities to the characteristics of these discharges, but this is on a smaller scale. This is only about 8 feet. Here's another shot of the same. Notice how the sparks attach to the side of the secondary. And you'll see areas of blue hue in between the blue-white streamers, which of course are the higher current discharges. It's almost like a sheet ionization. Here's that Model 7 coil again with my friend Jim Schaefer standing next to it for size. Here's the base unit of that, 3/8 copper tubing. Here I'm using colored plexiglass, a deep blue plexiglass. It's very beautiful. The nice thing about building Tesla coils, it's like building model airplanes or anything else. You can use so many different materials that will work so well and produce a very beautifully, strikingly vivid coil. The white discs are nylon discs, or rather dowels, that were purchased surplus. And the diameter of the lower primary, they're about 20 inches in diameter. Here's the discharge from that coil. Input power, about 5 kilowatts. 30-inch toroid on top, time exposure approximately 2 seconds. Jumping to a grounded rod that is sticking in the upper left here. Longest discharge off this coil, almost 9 feet. It's running with a synchronous rotary spark gap and 2 capacitors running at 0.04 microfarad. Yeah, that's 0.04 microfarad on that coil too. Notice the difference in the power arcs as compared to the air streamers. The tuning of this coil was affected, incidentally, by that cargo container. That's a portable storage container that you can rent. And because that's aluminum, it's all metal structure. When you get into larger coils, suddenly you find out that just because you think you have enough space, your coil doesn't tune properly. Things like something like a container or a wall, a plaster wall, a cement brick wall or whatever, will affect your tuning. So you have to be careful. What about power controllers? What do you do about turning on and off the power and adjusting the voltage and the current? Rack cabinets are an excellent choice. You can buy them surplus and you can refinish them. You can buy blank panels. You can buy these kinds of meters and produce a very beautiful and very functional unit. You can monitor voltage and current You can control all the parameters, and you really have a professional finished unit. And again, for not terribly much money. This is the back of that rack cabinet showing the variacs. And in my scheme of things, as in most people, what we like to do is use two sets of variacs, one as a voltage control and the other as a current control. And we'll explain why that is in another segment. Here's that rack cabinet that you saw off to the right, and there's a large secondary coil and a primary coil. And remember that 50,000 watt transformer and one of those capacitors. This is a system that's being put together, which has gone through several states of metamorphosis. This was back in 1975 when I first built this system, and you will see pictures of it discharging. This is that coil assembled. Notice that there's just a single corona discharge breaking out off of the top wire. It's not coming off the toroid. Anybody know the reason why?
Improperly tuned.
That's part of it. Improperly tuned is what the gentleman said, but there's another reason that's even more significant.
Toroid mounted too high.
Toroid is mounted too high, and it's too small in diameter. We have not moved the E field out far enough away from the electrical stress of that top turn. That was a 9-foot long corona that burned off the top turn of that coil. Does not make for a happy camper. Now, here's that same coil operating. That coil is 9 feet tall, 2 feet in diameter. It's number 10 wire, wound about 2.5 turns per inch. The toroid on top is 48-inch diameter with a 12-inch cross section. This is a single pulse, that is just zap on and off, just like that. And this is my backyard high voltage laboratory, so to speak. Here is the base unit of that coil looking a little bit closer. Notice how high up the primary is mounted up off the ground, and see the porcelain insulators that are used to support it up off the ground. The reason for that, when you build higher power equipment, things are not what they appear to be. You can't operate a coil this large on casters right down on the ground. Reason why? The energy radiating on that primary coil, a lot of it's being absorbed into the ground. You want to get all that energy into your secondary coil. The way to do that is to decouple it from the ground. Get that electrical magnetic field away from ground so that those lines of force will actually couple into the secondary. This is a discharge again. Remember that 30-inch toroid in the previous picture? It's now mounted on top of the 48-inch toroid, spaced above, and a corona point. These discharges here are about 18 feet long, and the input power is on the order of 10,000 watts of power from a 220-volt standard household feed. This is an aerial view of the backyard, and what you see with the white vertical column there is a 20-inch diameter aluminum ball and flexible aluminum tubing being strung across, and it's suspended over the pool, and it's hooked up to that other coil that you saw in the backyard. This is a close-up of corona discharge leaking off of that line. It's what I call a transmission line. It was an attempt to try a transmission line experiment to tune the coil so that the maximum voltage was not at the top of the secondary, but remote, out at the end of a transmission line. Again, just trying to replicate some of Tesla's experiments. And I used the pool for a ground plane. Works great. Impresses the neighbors, too. This is looking at the surface of the pool, and you can actually see where the sparks attach to the surface of the pool. Beyond that is reflected light looking back up at the ball, so you actually get a mirrored reflection. It's very nice to study spark discharge. These discharges are lightning-like. I used a hot wire ammeter in the ground circuit and measured in excess of 100 amps RF. And the resonant frequency here approximately 80 kilohertz. And my pulse repetition rate was 240 pulses per second. And the gap from that 20-inch ball down to the surface of the pool is almost 20 feet. Well, here I am backwards standing in front of the marker, which is right here in town. And the reason why I have these pictures in here is because for those of you who have not had the opportunity while you're here, and maybe you're visiting out of town, strongly encourage you to go down here to the corner of Pikes Peak, just west of Kiowa Street, and look at this. Again, apologies for the slides being backwards. I never heard of a slide projector that doesn't go inside out or upside down and backwards, but apparently at 3 a.m. this morning, maybe I was inside out and backwards instead. This marker is still there, and it is thanks to the fine people of the Tesla Society that makes that possible. Again, backwards, but the intersection of Kiowa and what's its name street? I can't even remember.
Wasatch.
Huh?
Looks like Wasatch.
No,
No, it starts with an
it
S.
should be Kiowa and Foot, I believe, but I'm not sure of that.
Kiowa.
Kiowa, that's right, thank you. And this is the area approximately where Tesla's laboratory stood. It's kind of an interesting thing. There's a lot of speculation about where exactly in town did his Colorado Springs laboratory stand in 1899. I'm going to get away a little bit, and we're running a little bit late, so I'm going to speed this up. Just a few pictures of the area. That fire hydrant seems to have some kind of a connection to what Tesla did, because as I recall from the 1990, and I think even before that at the 1988 symposium, there was some work being uncovered as far as the microfiche records in the basement of city engineering plans that shows the piping for the sewer system and so forth, and there's some reference there about some of Tesla's work. Is Mr. Golka in the room by any chance? Is Bob Golka here? Don't see him. Well, I know he's in the area. I included these slides because I had the opportunity to work with Bob from a period of about 1976 up through about 1982. And this is Windover, Utah. I include these slides here because for those of you who never had the opportunity to see what he did there, it's very worthwhile. And it is a testimony to his ability to produce big sparks. Since Tesla's time, to the best of my knowledge, nobody has produced more powerful or longer discharges than Mr. Golka has. This was Windover, Utah, and the Air Force hangar that was there. This was his control panel set up in that hangar. One needs to remember when looking at these particular slides that he was working on a budget that was very restrictive. So, again, using whatever surplus materials were available was the order of the day. His source of power was a three-phase, 150 kilowatt alternator, diesel-driven and mounted on the flat bed back of a deuce-and-a-half truck, an Army-type truck. And here is a view of the interior of the hangar, and true to Tesla's primary and secondary coil, you can see the heavy cable at the bottom, and the individual posts here without the wood, and then the individual wires forming the secondary. Now what Bob had done is he had advanced to a point to where he had to move the extra coil outside of the secondary. The hangar was large enough to permit him to do that. Another view of the secondary wire. That's 8-gauge wire, or 6-gauge. I forget if it's 8 or 6. It's either 8 or 6-gauge wire for the secondary. The primary, which you can see is going around the bottom there, and see how it's elevated up off the ground. That is 500 MCM welding type cable, so the actual cross-section of that wire is just over 1 inch in diameter, and there are 2 turns, but they're run in parallel. That's like 1 turn by filer, 2 turns in parallel. Same thing as what Tesla did. Here you can see that primary a little bit better. Again, when you're doing experimental work, you just try to get with the program and do what you can to get to the results necessary to obtain. So anything that will insulate reasonably well and get the coil in the proper positioning. And incidentally, the tuning, and we're going to talk about tuning, this is very significant because that bottom turn is so many inches off the floor. The primary is so many inches off the floor. The floor is reinforced concrete. It acts like a big ground plane. The spacing of the adjacent turns, very significant. You start changing one of these, even on a coil that's 51 feet in diameter, you start changing one of these parameters just to 1 or 2 inches, and everything goes to you-know-where in a hurry. It's amazing how high the Q can be of some of these systems. There's another view of the secondary, and looking at the opposite view of the hangar, and across the top here you see what is actually like a transmission line, a feed line. It connects the secondary to the extra coil, which Bob had moved outside of the interior of the secondary. That's where Tesla had his extra coil, right in the middle of that secondary. The reason why Bob had to move it is because he was building apparatus that was much more powerful than what Tesla had done. There's the transmission line coming across to the extra coil. Notice that it's helical and then conical on the top section. Also, you'll notice if you look closely that it uses sort of a basket weave type pattern. That's to keep tension on the individual strands of wire to keep them from sagging, but it also increases the Q of this resonator as a shock-excited helix. Very interesting process, and it worked very well for him. There's a view of the extra coil off in the distance. And you'll see a corona point sticking up to the upper left. That corona point is about 6 feet long. Now the height to the top of the rafters of this hangar is about 75 feet, as I recall, as a straight drop down to the floor. So as a spark gap from the top of the extra coil up to the rafters is on the order of somewhere around 60 feet. The capacitors that Bob was using, specially made for his project by a company that I think has since gone out of business, Capacitor Specialists Incorporated. And these were polypropylene film capacitors. And as you can see, he had a stack of them in a row there and was placing them all in parallel. The tubes feeding them was to keep the oil supplied. And notice how big those things are. Those things are actually about, as I recall, are about 10 inches in diameter and about 2 feet long. They weighed about 50 or 60 pounds apiece. And each one would hold about 3 or 4 gallons of oil. But then he was putting in a lot of power. Notice the transmission line. See how it leaks along in different places? Look at the extra coil. Notice how the discharges wrap around. They don't go straight down, they wrap around, semicircular. And we'll speed this along here. Another picture of the same. Now there's a power arc going from that corona point all the way up to the ceiling, and at the same time going from that corona point back to the beginning of the extra coil, and it's actually following that semicircular pattern. Plus all the rest of that corona all simultaneously. Imagine if you had a toroid that was big enough and you had an area large enough, the size of sparks that could have been made. I would easily think he could have exceeded 200 or 300 feet with this system with the right applications. This is a time exposure of approximately 2 seconds.
Wow.
And again, discharges going all the way from the top of the extra coil down to the ground. By the way, when those discharges hit the ground, there was so much power and so much current in those sparks, it was just like as if you took a pickaxe and swung it as hard at the concrete as you could. It would take chunks out of the concrete as big as a dollar size and a ½ inch to an inch deep, because it would superheat the concrete and it would just blow chips right out of the surface of the concrete. Another shot showing multiple discharges. He was able to control the repetition rate and also the amount of current, so he could obtain a variety of different behavior patterns, as I like to call it, from his coil.
No, are we seeing nodal points there on that transmission?
Yeah,
line?
you sure do. The question was, do you see nodal points on the transmission line? And that was something that was very hard to get rid of. It's kind of like camel humps. You push one down and 3 others pop up. You change one thing on the secondary coil, now your transmission line is no longer flat as far as voltage standing wave ratio, and suddenly you have a serious problem, and the wire just melts. I mean, it goes bang with one big de-arsonable discharge down to the ground, and that transmission line was about almost 16 feet off the ground all the way across. Well, here we are at the foot of Pikes Peak, and here we are at the close of the first part. Let's bring the lights back up. We'll take a 10-minute recess, and then we'll get into the second part of our presentation. Me and all of the symposiums that we've done. I was outside, and I was thinking, you know, that first carousel of slides, I had them upside down, which is correct, but I also had them backwards, right? So everybody was on the left instead of on the right. So I decided, oh, I forgot I've got to change that carousel of slides for the second part. So I'm back there feverishly changing slides. And then Jim turns around and he says, well, what are you doing? I said, well, I'm changing the slides. He says, I already did that. You can't win. Okay, are we all set now? Hopefully these slides will be right side up, because most of these are technical illustrations. In this second part, we're going to discuss spark gaps and spark gap design. And we're going to go through it pretty rapidly because we've got a lot of time to try and make up.
Can you set that?
Oh, yeah. It's black.
I'll get it.
What do we... All right, if we may begin, let's bring everybody back in and close the doors and turn the lights down, please.
I think you've got a clear field there.
Very good, thank you. Can we bring the lights down, please? Now, for the sake of taking notes and so forth, I think that we should leave these lights on. Let's, Tom, let's put, there we go. I think we'll be able to see everything okay. Okay. Oh, let's see, who do we have here? I can't quite make that out. Ross, Doss? Thornton Doss, is there a Thornton Doss in the room? Somebody has left their Discover card behind.
Dinner's on Ross.
Sorry. Okay.
Maybe it's for donation.
Give me back, don't worry. $200 a month.
All right, here we go.
That's the way to do it.
Oh, is the, I think the lamp on, light on, the projector, please.
See where it is.
Hey, there we go. All right, now let me back that up a little bit. Yeah, part 2, okay. Hey, so far so good, folks. Can we focus a little bit, please? Jim? You have to manually adjust the focus so we can save time.
It's the other knob,
It's the
Jim.
knob in the front there. There we go. Schematically represented here something that we talked about, which is a safety gap and protecting the secondary of the transformer. Notice that it's 3 balls arranged in a triad, equal space distant. The secondary schematically represented as a floating secondary. Neither side of the high voltage secondary is referenced to ground. The third electrode is the odd man out, going to ground. You have to be careful with this kind of an arrangement because if your core of your transformer is not also grounded, then you could create a feedback circuit if you do get a spark across there, and that that feedback voltage could actually cycle through the transformer into the primary and burn it out, or else burn out something else in your wiring. I'll tell you a brief anecdote at this time. Dick Aron, I mentioned him in this coil, and he worked for Dr. Irwin Moon. Many of you have heard of the Moody Institute of Science, the Sermons in Science. Dick Aron worked for Moody building a number of coils, and at one time that one coil that you saw in the beginning, which was the Griffith Park Observatory coil, Dick talked the director of the observatory into giving him the other secondary coil for him. He took it down to Moody's lab, which was in Los Angeles, and took some coax cable, some RG8 coax cable, and just wrapped a couple of turns around the bottom for a primary. And he had a capacitor bank and a rotary spark gap and one of these Amatran plate transformers almost as big as this pole pig. But he didn't use any current limiting. He hadn't learned this business about non-saturable core transformers. Now in the Moody Institute, there was an audiovisual room where they did all kinds of tape duplication and so forth. Thousands and thousands of dollars of Wollensack and Reese, I think it's Reese or I forget the manufacturer's name, all this duplicating equipment. Dick threw the switch. Big power arc came out from the secondary coil all the way down to the ground and hit the primary feed line. And there was no safety gap. And that created another feedback voltage loop into the AC line, which burned out all of Dr. Irwin Moon's equipment. Dick was fired after that. But a safety gap is what saves your secondary, and it can also serve to save your capacitor too. And the design of the gap is important, the spacing of the gap is important. There's a relationship between distance and diameter of the balls if you use this kind of a ball gap. Field distribution. Remember I talked about if you want to learn a lot about the phenomena that takes place, experiment with electrostatics. Read books on electrostatics. The early experiments in electrostatics. You'll find the electric lines of force represented in a simple ball gap are approximately what you see here as far as the lines of force that count. These are electric lines of force. Notice if you go to a needle gap how much it compresses those lines of force down. The process is such that ionization, which is where you create a path across from one electrode to the other and make it conducting, create the spark. In the case of a needle gap, there's much greater electrical pressure at the tip than at something like a round curvature of radius. This is something that Tesla talks about, and it's something that's very important and necessary for spark gap design. Many of you have seen small Tesla coils that use like nails, and the sharp points of the nails forming the spark gap. Very inefficient because it breaks down at a very low voltage, and it also stays ionized past the point where the capacitor discharges across the gap. What follows after that? A low frequency arc in the case of a 60 cycle type transformer. And that actually detunes and decouples your Tesla transformer, your primary secondary circuit. And it can manifest itself in ways that you don't understand until you really start to look at how these things function. You might think, well, my transformer isn't properly tuned. I've got to add more capacity to the primary, or I've got to add more capacity in the capacitor bank. When really all that is at fault is the gap is not functioning properly as an on-off switch. Remember, the spark gap's sole function is what Tesla refers to as a brake or a commutator, meaning that it is a time-sharing device to allow the source of power to charge the capacitor, and then allowing time for the capacitor to discharge that energy and ring the oscillatory circuit of the capacitor and the Tesla primary coil. This is right out of early induction textbook design. And this gap appears, incidentally, Jim, in Twaining's book. This is out of Twaining's book, as I recall. Notice that it's a needle gap. It's very ornate, it's beautifully designed. But I'll tell you what it's good for. It's good for experiments with induction coils and just simply making sparks. It is not good for any design of any Tesla coil, I don't care how small. Many of you may remember an article that appeared in October 1961, Popular Electronics. It was called, not little TC, it was called...
TC.
No, that was in 1964. It was the first article that I ever saw in print in the popular literature on the design of a Tesla coil. And it used a Model T Ford spark coil. It had a 4x5 inch glass plate capacitor. Secondary was only 2.5 inches tall, 3/4 inch in diameter. Beautiful little coil if you build it properly. Used a needle gap. Would have been much better off with a small ball gap. Would have gained a lot of power without having to change the size of the transformer or the amount of input power to the Ford induction coil, which was, in my case was just a 6-volt battery. Best spark I could get off the secondary of that coil, just about 3/4 of an inch. It took me years to figure out, well, gee, the capacitor was the right size, the primary and the secondary were the right size, the Model T Ford spark coil was the right size for that small of a resonator. So what was the problem? Why couldn't I get the 1.5 inches that the article talked about? The spark gap was breaking down prematurely. Another form of spark gap. This comes from a text of early wireless telegraphy. Notice that they're flat, surfaced zinc electrodes. So in terms of cross-section, it appears just as a circular disc. Superior. And the reason why is because the electric field is uniform except at the edge around those electrodes. And being zinc is important too, because this kind of a gap could actually take a fair amount of power, probably 1 kilowatt or 1.5 kilowatts, and work very well even though it is only a stationary single spark gap in an oscillatory circuit. The zinc works to absorb the energy where the spark impacts the surface of the metal. And you have to almost get into metallurgy in order to understand, gee, even though there are things I don't see happening there, they're truly happening. Down to molecule size on the surface, little surface undulations or perturbations of the surface that are actually being perturbated by the spark going across, creating microscopic ionic breakdown. And what's important about that is, again, for a uniform voltage distribution across the gap, whether it's a single gap or otherwise. So electrically, this is what that gap you just saw represents. Fairly much uniform lines of force. What happens, though, is, well, we got one backwards. Sorry about that. Notice that what I'm representing here are two stationary gaps. The upper set, where B and D are proportionately larger at D and smaller at B, as compared to the second illustration. Electrically, as far as air pressure is concerned, these two gaps may break down at approximately the same voltage. The difference is that the rise time and the amount of power sent across the spark gap of the lower set would be superior to the upper set, because you've minimized the airspace that gap has to leave. and still it will not pre-ionize. You want that to arc across or spark across and then quench or open up instantaneously with no lingering lag time, no trailing edge of the spark hanging on. And we're talking about something that goes down into the microsecond range. It's stuff that you can't appreciate unless you have a very high-speed oscilloscope and start studying this sort of thing. What I'm illustrating here are pockets of ionized electrons. Many of you have probably read books that show the process of how a step leader of a lightning discharge finally creates an entire circuit path, then you get the return stroke of high current. Same thing happens with any spark gap, it's just on a smaller scale. Remember that theory and apply it to the design of your spark gap. You don't want pre-step leaders. You want it to wait until the pressure builds up to its maximum value, bang, it fires across the gap, and then you commutate that energy effectively, and you want then to have no more lingering ionization. This is the process of those linking up. And here's what happens after the fact. If you don't use the right kind of material in the right size and have enough heat sinking capability to the surface of your electrodes, hey, they feel cold to me, they're not hot. And as you know, when something gets hot, it ionizes much easier, especially in the form of an electric spark on a metal surface. But in the microscopic range of molecules across the surface, that can still be causing pre-ionization or lingering ionization after the spark gap has functioned. And it makes a heck of a difference in the performance of your coil. Here's what is the difference of a representation graphically of an electrode that has a cold surface regardless of its material or size or shape as compared to one that's hot. So those electrons that are freely near the surface of the hot electrode will give you more problems about breakdown and not proper spark operation in your primary tank circuit as compared to a cold electrode. Back to mechanical interrupters, and back to Tesla, and back to Tesla coils. This is a commercialized form of a mechanical brake for interrupter. Tesla perfected a whole variety of these, which you'll see in a number of other papers presented here at the symposium. What's interesting about mechanical interrupters is that they're only good up to a certain value of power and repetition rate. And I don't think anyone has succeeded in doing anything better than what Tesla did. Cross-section illustration of one of his mechanical interrupters. But only good for low voltage operation. This was his high-speed mercury brake and was capable of, I forget, Ken, exactly how many...
100,000 breaks per second.
100,000 breaks per second. And I think that was like, what, 20 inches across in diameter? Mercury being forced out. So mercury was going through and making contact with a rotating internal mechanism. There are other people, including Ken and Jim Corum, who will be talking about a lot of these things in much more detail. Another form of spark gap. Well, what do you do to deionize that spark gap? Remember, you don't want it to ionize. Magnetic field in the case of two electromagnets here, and the balls being able to be rotated so that there's always a polished, smooth surface instead of a rough surface. And that's what you want, is a polished, smooth surface on the face of your electrodes. The magnetic field helps to deionize the gap. It helps to blow out the spark after that initial breakdown, which is what you want. Another example of that, and these illustrations come right out of Tesla's writings, and they're available in the bookstore in a number of his publications. This is kind of interesting because here hydrogen was being used to pre-ionize this gap, but it was for a special application. Until I understood more about what Tesla was intending this kind of gap for, I thought, well, gee, that's just an air blast across that gap. Not so. And it wasn't intended for a spark gap oscillator circuit. It was intended for a continuous wave arc type of application. But you have to read very carefully the description. Here's a number of electrodes in series, and they're in sort of a conduit, if you will, where an air blast could go across them or just be ambient air pressure. But by using multiple stationary electrodes, that's better than just having a single set, and that's why I showed this illustration. So as you go to higher power, and even medium or low power coils, spark gaps in multiple series as stationary gaps will always perform superior to a single gap. That's something to remember. Let's talk about efficiency. Well, I want to build the most efficient Tesla coil I can, regardless of whether it's tabletop or floor or the big kahuna. What do I do as far as spark gaps? How do I decide the design? Small coils can get away with single stationary spark gaps. Medium-sized coils can get away with series multiple stationary spark gaps. Let's talk about what's next best. Here's that Marconi type discharger. Can you make it out there? It says figure 50. Notice there's two stationary electrodes. There's a disc. The electrodes are double-sided on about the periphery of the disc. The motor drives the discs, rotating these rotary electrodes around and coming in close proximity to the stationary electrodes. Other designs of rotary gaps. Many different iterations, all designed to do the same thing, to effectively allow a condenser discharge or a capacitor discharge to dump its energy or oscillate and ring into the primary circuit. Parallel gap. Notice the parallel gap at figure 49 as compared to the air blast gap. Believe it or not, 49 is a more effective gap than the air blast gap, where you have a small cross-section of the sparking surface of the electrodes. Commercial versions of those illustrations. A quench gap, a coaxially mounted concentric quench gap on the upper left. Upper right, a Benwood super gap. These were commercially made products in the heyday of wireless telegraphy. Lower left-hand corner, non-synchronous rotary gap, two stationary electrodes, but notice that those are like paddle wheels. That's flat discs. And on my gap that I have displayed up here, you'll notice a similarity in the concept. We'll talk about that in a little bit as to size and shape of rotary electrodes. So remember, stationary gap, multiple stationary gap, non-synchronous rotary gap, synchronous rotary gap, quench gap. Those are ascending orders of efficiency if they're properly sized and shaped for your equipment in terms of maximum power transfer from your power source into your capacitor and maximum power transfer from your capacitor into your Tesla transformer. Here's an example of a poorly designed, beautifully built, synchronous rotary gap. Can anybody tell me what's wrong with that illustration? And Jim, can you sharpen the focus a little bit?
The per contact or
Right, well, keep going, Jim. A little more.
Bingo.
Okay. Yes, sir? You said?
per district plates. Well,
Exactly. Dwell. Yes, you hit it right on the nail. Dwell time. Everybody knows about distributors in engines and about dwell time and dwell duration on the distributor, right? Same thing with the Tesla coil. The more tightly coupled your Tesla transformer is, that is, the physical relationship between the primary and the secondary, necessarily the shorter the dwell time, that is, the total length of time that your spark gap is eligible to discharge, must be. The reason for that is because when you transfer electromagnetic lines of force from the primary to the secondary, and this guy starts oscillating, then it wants to do the reverse of that. It wants to act as a step-down transformer. It wants to couple that energy back into the primary. And if your gap is still ionized or is still a candidate for reionization and breakdown, you're detuning your coil. You're actually losing energy that was otherwise going to just sit there and ring until it dies down in the secondary. So what's wrong with this gap is that it might do well as a rotary rectifier for converting AC to DC, and that's how they did it in the early days. And that's how Tesla did it at Wardenclyffe. He used rotary rectifiers. But it's terrible. I mean, the dwell time on this, even though that disk spun at 3,600 RPM, must be on the order of 10 milliseconds. Way too long of a duration for any kind of a practical Tesla coil application. An example of a commercial rotary gap that's wholly enclosed, it's what is called a rotary quenched gap, because here we have disks of broad cross-section that are rotating opposite each other in a pressurized or semi-pressurized environment, or at least to the point where the oxygen is burned out and nitric oxide is all that's left, which does not support ionization past initial oscillatory breakdown. Oftentimes quench gaps are used just for that purpose. They don't have atmosphere in them, not after they have been cured or healed. They have the nitric oxide that is left behind, which is after all the oxygen has been burned off. When you have that, then it's like the next best thing to having a pressurized gap of sulfur hexafluoride, which is what most people do for modern day high power applications. Another design of rotary spark gap. Again, this is out of Bircher's book on wireless telegraphy. What's nice about these is that they're ornate, they're beautiful, you can build them, they will work effectively, but only to a point. When you want to go for higher power, you really need to consider, and what's unfortunate is that, as in many of Tesla's illustrations in his patents, if you build it exactly like the patent says, you don't get the performance that was intended. Merely what is shown here is just like in a lot of those patent illustrations. It's showing a concept. Notice that there are 4 stationary electrodes and 5 rotary electrodes. Descartes, when he built the rotary gap that's on the base of this coil, did exactly the same thing. He had 7, I believe it is, rotary electrodes and 6 stationary electrodes. And that gap was set up to be a synchronous gap, too. Here's something that's very interesting. Notice that it shows a cross-section of the 2 stationary electrodes. See, they're only very short in cross-section, whereas the rotating disc, they're very broad. So effectively, it's no different as if the stationary electrodes were just as broad. This kind of a gap would give you a very long dwell time. You can use gaps of a long dwell time if your primary to your secondary is not very tightly coupled. And that translates into the physical size and the relationship of spacing between the primary and the secondary. Here's another view of that gap. Ajax. Great for wireless telegraphy work, but not very effective for continuous wave. What is continuous wave? What are we doing with continuous wave? We want to put as much energy from the primary into the secondary, and we want it to stay there. We don't want that energy coming from the secondary back out into the primary. It's all up to the spark gap to accomplish that. Once it transfers the energy to the primary and then into the secondary, that gap has got to remain open until the next oscillatory pulse comes along. And then if you cram those pulses close enough together, this thing sits there and looks like an almost continuous wave oscillator, which is the highest efficiency. This illustration is very important. This is a diagram illustration of what Tesla did right here in Colorado Springs in 1899. He writes about it in his Colorado Springs notes. The idea is that across A and B with the unequal sized balls, that the electrical breakdown was not sufficient until the rotary disc at B had its rotary electrodes in proximity to the stationary electrodes on the inside of that box. To my knowledge, this is the only illustration, and Tesla gives precious little information, but what he does give is very vital. The idea of the unequal electrodes on the outside is straight out of electrostatic theory. Notice that the largest electrodes, which would be the continuation of the primary resonant tank circuit, are on the outside. They're not on the inside. That's also significant. Representation, somewhat, of a non-synchronous rotary gap as far as amplitude and pulse wave trains in the primary circuit. Even though it's hand-drawn, notice that the dotted line represents the envelope of the oscillatory wave trains, and see how non-uniform they are. Why a synchronous rotary gap is more efficient than a non-synchronous rotary gap. The ability of trying to make the oscillatory wave train pulses of a higher amplitude and more consistently uniform. And in terms of what they were doing with wireless telegraphy, they were really doing 2 different things. They were trying to get a constant, detected audio note. The sound of a receiver in a wireless transmitter with a non-synchronous gap was a crashing, noisy sound. But with a synchronous rotary gap, you could have a steady tone. Here is a sine wave, 1/60th of a second represented. Notice the little tick marks. Those would be points of commutation that might be set up for the primary circuit oscillating with a synchronized gap. A non-synchronized gap would give you random oscillations all along. So some of your pulses are of high amplitude and some are of low amplitude. You're wasting time and power with a non-synchronous gap. Synchronized gap being far superior. An example of a commercial rotary disc discharger. Notice that the rotary electrode points as well as the stationary points are pointed. But this is special application. This was direct shaft driven from a 500 cycle alternator. And there's something like 60 points on that rotary disc. Not typical application. This is what that actually is. The rotary disc discharger is on the outside and the alternator and DC motor driving the alternator for 500 cycle operation on the left. Remember what I said about dwell time and about eligibility to discharge? I'm showing a stationary electrode on the left, and on the right is a rotary electrode that's coming by at a fixed velocity. Well, if I bring that electrode by at 800 RPM, then it's going to be in proximity of that stationary electrode for a much longer period of time than if I bring it by at 6,000 RPM, right? So what is necessary is not necessarily more rotary electrodes, but maybe a shorter dwell time. That's why if you want to run non-synchronous, if you run a DC motor and run it with a DC rectifier with a little auto transformer like a variac, so you can vary the speed. As you power up your coil, you're going to see the difference in the output of the discharge. It'll be thread-like and thin and very sporadic and sort of sputtering, and then it'll start to sing. And finally, you'll start to see corona streamers coming out that are like long tendrils. And you'll find that the point of the longest, brightest discharge is not commensurate with the highest repetition rate or the highest commutation rate. But it is at a point where it is synchronous with the AC frequency that's charging it and is allowing the capacitor to discharge the maximum amount of energy with each pulse. Here's an example of a gap where the stationary electrodes and the fixed electrodes are both half-inch diameter, and the motor's running at 3,600 RPM. You cannot really change the dwell time or duration with this. You can only change the dwell index point.
Does that have silver dimes or something on the...
No, no. The question was, what is the surface? That's thoriated tungsten. And that's very important for a medium or high-powered coil. This is a close-up of that showing that same apparatus. Incidentally, the stationary electrodes in this case are solid thoriated tungsten rod that sells for about $60 for a 2-inch chunk of it. It's very expensive, but it would last forever. Another view of the same. Notice the discoloration on the lower part of the stationary electrode on the left-hand side there. That's oxides that are actually building up on the surface of that metal due to the flame out of the spark, which tells you the direction of the wheel is rotating. It's rotating clockwise with respect to your point of view. Remember the quench gap. An early form of quench gap using air. So what are we doing here? We're simply spreading out the spark. It's like taking cookie dough and smashing it out flat, increasing the surface area. So now instead of a few thick sparks across a short cross-section of area, we have many small sparks over a very broad area. And notice also that the cross-section shows that there are heat fins or heat sink areas to increase the surface area for heat radiation. Why? To keep the surface of those electrodes cool, to keep them deionized, and have many sparks of very high power over a broad surface area. A very effective gap if you want to take the time to machine it. Schematically represented about a quench gap or a multiple parallel plate stationary gap. Again, the electromagnetic lines of force are fairly linear and fairly uniform across each of the sections if the gap spacing is equidistant. But even if it's not equidistant, those lines of force are still uniform. The only thing that changes would be the voltage gradient between V1, V2, V3, V4, V5 to Vn, however many gaps you run in series. Very effective method of quenching if you don't want to go to a more expensive alternative. Commercial version of a air-blown quench gap. The air blower on the left blows air to cool the cooling fins, and there are approximately 20 discs in series there. Notice the adjustable taps. The adjustable taps for several reasons, not the least of which, these gaps had to be taken apart and physically cleaned on a frequent basis because the surface of the metal of the sparking surfaces gets contaminated. The center part of that disc represents the actual sparking surface. The groove represents a relief so that it concentrates the spark only in that center section. Then you see the cooling flanges on the outside. Well, when you first put a quench gap together, maybe it doesn't fire on 10 segments in series. So you have to go down to only 2 segments. And it fires like crazy, and then all of a sudden it starts drawing too much current. Then you start adding more and more gaps in series. And eventually, if you've got your whole series airtight, then the next thing that happens is that you finally burn out all the oxygen in all those segments. Now your gap is cured and it's ready for operation until it has to be cleaned again. Cross-section diagram of the previous illustration. Electrodes. Gentleman here asked, well, what is the surface of the electrodes? Remember that I said you want to keep the electrode surface hard and smooth and as low temperature as possible. Represented from left to right is the solid thoriated tungsten rod stock, and here is stainless steel, and on the right are electrodes that someone came up at the last break and told me about arc welder supplies. Now, in arc welding, when you talk about TIG or MIG welding, that is tungsten inert gas or metal inert gas, guess what they use to start those arcs? Tesla coils. Somebody says, well, what's the commercial application of a Tesla coil? Go to any electric arc welding shop that uses TIG welding or MIG welding. I'll show you a Tesla coil. What do they do for the spark gaps for those Tesla coils? You're looking at them right on the right. They're expensive, but they are available, and they work extremely well for power levels up to about 10 kilowatts. A view of the cross-section of one of these solid thoriated rods, thoriated tungsten rods. Again, very expensive. That rod is about 50 bucks. This is an assembly of a stationary electrode. Here's one of those screw-in studs with a thoriated tungsten face, a piece of brass rod stock that's been turned to create fins for heat radiators. It's a heat sink, and then the brass rod mounting behind it. Well, we got another one back there, Jim. That's okay. Everybody just use a mirror and look at the screen this way. What was I talking about constant amplitude and getting those pulses closer together? If you read from right to left, as they do in some countries, points of starting commutation, IR drop after commutation, that refers to the voltage that's present across your capacitor and your power supply, notwithstanding the AC sine wave that's charging it. So if this represented 1/5000th of a second from time 0 to time n, and if you put in enough current, even though you're 60 cycles, you could get that many breakdowns in that short of a period of time. But then you have to address the issue of your capacitor to be able to absorb that much energy, which means you have to have more surface area. Remember I said that you have to have more surface area if you're going to put in an awful lot of power. You can't put a lot of power into a very small surface area capacitor and expect it not to blow up. Well, this one's correct. 2 sine waves shown. So now we're talking about 1/30th of a second. And the arrows are indicating points of starting commutation. This is the ideal case for a synchronous rotary gap. This is where you transfer the greatest amount of energy from your transformer to your capacitor and then to your Tesla coil. There is a surface of a quenched spark gap. And I'd like to step up here briefly and point something out. If you were to look closely, you'll see that there are some areas that are sort of discolored, especially in this region here. That is a thing called spark migration. I characterize it as such. That's the area of that surface of that disk, even though it's machined perfectly flat to within 1/1000th of an inch from the opposing disk that was facing it. Sometimes the spark tends to just naturally favor this area of the surface mostly. And that's where the most roughness and perturbation of that surface takes place. Well, the problem with that, if you were to look at it under a high-power microscope, is that you'd see something that looks like the surface of the moon. Now, you can't feel it with your fingers. You can see it. It looks like a rough texture as opposed to a polished, smooth surface. The difference is that all those rough edges is where you get pre-ionization breakdown. And it actually destroys the efficiency of your quench gap. So you have to get back to having a smooth surface. Remember that the time for each primary oscillation is very small, and you want that to commutate the energy into the secondary coil, and then you want to allow the secondary to ring out. It's all up to the spark gap to do this. Finally, if you want to experiment and have your access to small squirrel cage fans or something of that nature, you can build a pressurized air gap. Now this is an illustration of a triggered gap, but it's actually using pressurized air, again to deionize the gap. So in summation of this portion of the presentation, remember that you must build a gap that commutates effectively. It turns on and turns off completely. We'll take another break and then we'll come back for the final segment. You can bring up the lights, please. A full wave, that is a bridge rectifier. And this wheel has been borrowed from a surplus pulsed radar forming network. The disc is aluminum. These rods, which are about an 1/8 inch in diameter, are solid thoriated tungsten. Remember the illustration of the Ajax gap, the rotary gap that you saw? These are solid 1/2 inch by 1/2 inch by 100,000 inch thick tungsten electrodes. And if you were to see this, looking at it head on, you can see that the amount of time that the stationary electrode has to wipe physically across the space of the stationary electrode is very minimal. But if I change and adjust this and rotate this in this fashion here, I now have a much longer period of time where I have the possibility of candidate sparks jumping from here as it passes there, assuming I had a constant velocity. Now if I change the velocity, what am I doing? I'm changing the dwell time, but I'm also changing the pulse repetition frequency, or PRF, because I'm now going faster. And even though I'm going faster and the velocity is greater for each electrode going by, I have so many more electrodes that there is an almost universally adjustable range of pulse width duration and pulse repetition frequency with the gap of this design. So if you build a gap that has this kind of an electrode assembly, even if you don't have access to thoriated tungsten, what you can do is you have a universal gap that you can use for testing almost any size coil up to about 5 kilowatts. And you can change the pulse repetition frequency, you can change the dwell duration, you can change also the amount of pulses per second. And what I'm going to do is just leave this like this and show you that in a gap of this design, what's very important is to have it very well balanced. This is why machining is so important. Right now that motor is running maybe at about 20 volts AC input, and it sits there. Virtually no vibration at all. And yet you can run it up to 10,000 RPM. The reason why it rotates like that is because of the torque. There's a tremendous amount of inertia built up here. I'm reminded of a spark gap of the same kind of design, only a much larger size, that Mr. Golka used up in Windover, Utah, where it was spun up to a very high speed and it flew apart. And a chunk of it went into the concrete and blew a hole in the concrete, very large in size, and another chunk of it went out right through the corrugated roof of the hangar. But a gap of this nature is very nice if you plan to build a variety of Tesla coils, because it gives you an almost infinitely adjustable gap.
How many points are on that wheel?
This one here has 2, 4, 6, 8, 10, 12, 14. So really, in practice, when you're using 60 cycles, and if you're using a neon sign transformer, I found that a speed only that slow will give you the optimum discharge. What I had hoped to do was to be able to bring here a Tesla coil, a transformer, and a capacitor bank and hook it up with this. I ran out of room. We brought over 10,000 pounds worth of equipment in one truck, and there wasn't room to bring everything else.
See the show tonight.
I simply wanted to be able to show you this gap, to show you an idea of gap design. These discs can be found surplus, mostly in military scrap yards and that sort of a thing. And if not, you can build them. They're not that hard to build, but you do need access to a good lathe, and probably it's a good idea to have a vertical end mill with a rotary index head so you get precise spacing around the periphery. Remember the illustration that I showed you of a stationary spark gap? Believe it or not, this is from a arc welder. It has thoriated tungsten discs. They're about 3/8 of an inch in diameter, and it's adjustable as far as the distance between it. And these hex metal pieces here serve as heat sinks simply by the mass of the metal to keep them cool. But a gap like this will only work up to a certain power level. If you start putting in more power, these will heat up. The surface will remain hard because it's thoriated tungsten. So you won't have the rough edge problem, but it will get hot. It'll get so hot that it'll ionize, and it'll actually destroy the performance of the gap. The only way to improve that would be to put this in a pressurized atmosphere, or to enclose it in an atmosphere of nitrous oxide, or at the very least put an air blast across it. What we have here, and I'm going to ask Brent Turner and Pete Miller to come forward. Brent Turner has built two coils here. One is a spark gap driven coil, right here, and the other is a vacuum tube driven coil. And what's interesting about these, and I'm going to let him explain the efficiency of their operation, and I know that the gentleman with the camera would like to take a close-up. So possibly what we should do, can this be moved?
Yeah, everything.
All right. Why don't we clear this off here?
I was going to do the spark first and illustrate your concepts of the gap.
All right. What I'm going to do is let Brent here explain the operation of this equipment and this equipment here, and then we'll talk about the operation of this equipment here.
Oh, pardon me, Bill.
Pardon me.
Well, getting back, Bill covered a couple of interesting and very important topics with the slide presentation, particularly in the spark gap. For those of you that did come forward and look at the equipment, you will note that number one, I have a multiple element gap in this coil. Number two, it is of the flat parallel nature with a large surface area. And it does quench very well. When I turn this on in the dark, if you pay close attention, you'll actually see the quenching effect occur in the gap, where the sparks will not fire in the same place all the time. They will actually twinkle over the entire surface area. Also, this coil is somewhat loosely coupled. Several other parameters. Notice the copper refrigeration tubing for the primary design. One interesting thing on this coil, though, is the relatively small surface or terminal capacitance. The reason for this particular, or in this particular event, is the fact that this was close wound with a magnet wire. There is a considerable amount of distributed or planar capacitance in the secondary. So therefore, it does not require as much terminal capacitance to bring the coil into tune. Go ahead and, well, it doesn't quite meet it. There we go.
Can we have the lights, please?
This particular coil is powered by a 9,000 volt 30 mil neon sine transformer. Total system capacitance is approximately 0.01 microfarads. It's a wrap and fill mylar. The secondary is about 14 inches tall. On a good day, I can get a 14-inch discharge.
The alarm has been investigated and you will be advised when the all clear has been given. Thank you.
I haven't touched it. My grandpa is a smoke that's still there. Oh.
The third biannual International Tesla Society Symposium. We, that is my associates and I, were across the street at the Red Lion Inn, and they have a fire alarm system very much similar to this one. Well, a similar event occurred there as has occurred here. Now, I don't know if there are elevators in this building. I assume there are.
Yes, sir. They're all on the ground floor.
And I would imagine that if there were people in transit in those elevators, the elevators just stopped right where they were. And everybody's panicking, and we're probably all going to have a lot to talk about. So this has occurred before. Now, I will tell you that before we started this particular workshop this afternoon, my associate, Mr. Brent Turner here,
The one responsible.
plugged this coil in and fired it for about 1/4 of 1 second. It went bzzz, and he said, yep, it works. That was that. We have fired off this coil and had no trouble. I'm a little bit gun shy about even firing this coil.
We'll just do it while the fire department's here.
Well, the fire department's still here. I suppose that's okay. And I apologize for the interruption. This was certainly unintended.
Please don't have them edit it out, so we'll
Yes, it would have been. Well, I think we had a pretty good lead into the show as it is now. Thank you very much.
Go to the high school tonight, and
Well, considering as how it's 3:30, and since we're supposed to be out of here by 4 p.m. anyway, and who knows, maybe the fire department will kick us out even earlier than that, what I would like to do is modify what we had intended to do. You're discharging.
Pushing fate, aren't we?
yeah, if that's an ionization detector.
Yeah, this is CW though, it's not Impulse.
Yeah, but if it's an ionization detector, it'll detect the ozone.
And it's ozone, you'll get the...
Something for you all to learn about building Tesla coils. Watch out for fire and smoke detectors. They can be hazardous to your what? Yes,
Nervous system.
your nervous system, that's right.
Bill, does
Yes.
it mean that we shouldn't operate one of these devices in a laboratory?
Attention, ladies and gentlemen, the all clear has been issued, and you may re-enter the hotel.
You know, I can't think of any better publicity than a stuff like this. I mean, everybody in this hotel will know what the International Tesla Society is all about.
We will never be allowed to come back.
Yeah, really.
At least you didn't burn out the main power plant like Tesla did.
That's true. This,
Attention, ladies and gentlemen, the all clear has been issued, and you may re-enter the hotel. We apologize for the inconvenience. Thank you.
There are no smoke detectors in the gym, right?
Grant, please do me a favor. Thank you. Lady and gentlemen.
Actually, there's two ladies here, Bill.
Oh, excuse me, where's the other lady in the house? I see her, okay. Thank you very much. Oh, here's the fire department.
Oh, maybe you'll...
Fire it up.
It was an accidental trip. We were just running our small little spark gap Tesla coil here, and it sent a false signal to the detector. There's no fire, nobody's smoking.
Attention, ladies and gentlemen, the all clear has been issued, and you may re-enter the hotel.
Go ahead.
We apologize.
Yeah, let's fire it up. Turn off the power, show what happens. Yeah, turn off the lights. Fire the big one.
Well, I did successfully fire the big coil without any problem earlier, so I suppose we could try that since the fire department is here to watch.
Bill, the engineer, is thinking about changing the smoke edge. Maybe we want to wait?
Well, I don't know as if that would necessarily make any difference. There certainly weren't any direct strikes or anything else involved.
Open the door. Yeah.
What do we have going here?
We had a...
Crossover.
No, that's wired incorrectly.
Everything should be wired correctly.
But it's not our...
Shorted there somewhere.
No, it's
Oh, I see what the problem is, yeah. Okay, here we go.
He's a little more trusting than I am.
Okay, I got that.
It doesn't like the brand.
Well, now we just tripped a breaker.
But it didn't set off the alarm. Face it, Brandon doesn't like you.
Right frequency. I guess.
They should invite the fire department.
But at any rate, just briefly, notice what was happening here. We were just testing it. This is a tuned receiving coil. And it does illustrate the wireless transmission of energy and tuned reception as Tesla had originally proposed.
You have the free flow ground at the base.
Yeah, it was just, this is third wire ground, it just happened to be convenient. I could ground this anywhere in the room and do the same thing. You can also put this, unfortunately, too high a wattage bulb. I forgot to bring my regular bulb. But by putting this in series with the ground current, the ground lead, the RF ground current would be sufficient to light this bulb. I have lit a 15-watt bulb in the ground connection using this system 6 feet away.
We'll go through that demonstration again. You want to see it?
You want to see it? They got this demonstration going on. You want to see it? Maybe the next time you should do some tape for it.
Actually, I'll tell you what it is.
I think what you do is you hook the discharge
This
terminal
coil here,
directly.
the resonant frequency of this coil here is probably creating harmonic structures that the preamp circuit on that ionizer is picking up and saying, uh-oh, it's time to go off.
Well, we had to disconnect the one at home. We was running ours in the garage. We had to disconnect it totally. But we did find out it did turn the microwave on.
Well, mine kept opening and closing the garage.
We did a show several years back in '88 where we used one of our other gentlemen's large coils, and we got all set up on the stage. There's 1,700 people in the audience, and I said, "Okay, lights off, please," and the stage lights go down. We fired this thing off, and all stage lights came back up. And I asked, "Do we have lights off, please?" And they said, "They are off." Oh.
Well, what Pete Miller's talking about here is very significant because when you go and do Tesla coil demonstrations, you run into situations like this.
Will you run that thing again so we can see what's going to happen? You sure you want to do this? We might have
But we don't want another evacuation drill message sent throughout the hotel.
5 to 3, they're going to go ahead and run their machine again. On the button.
Kill the light.
You touch the switch. You killed it, Brent. Well, now it won't work at all. Good. You killed it. All righty, they run it, Oz. Everything seems to be okay.
I still wouldn't trust it.
It'll take you, what, a minute to replace it? Replace it.
Well, folks, I'll tell you what, we really only have approximately 25 minutes anyway. You have briefly seen the discharge. I know you'd all like to see a lot more discharge. We'd love to do it for you. The problem is that I think I'm a little gun shy right now. So let me simply point out several things to you here, and we're going to open this up for a question and answer period and try and wrap this up by 4 p.m., which is approximately 26 minutes from now. What Brent was starting to tell you about this is very significant. He mentioned about the small terminal capacity as opposed to the great amount of distributed capacity. The same thing holds true for this kind of coil. Well, what does that mean? It means that the inductance ratio is very great. When you go to higher power coils, you don't need this kind of inductance ratio. Moreover, if you do that, what's going to happen is that you're going to have short breakdowns along the windings. because the voltage gradient builds up too high in too short of a distance. And there's no way of insulating that kind of a coil with that kind of a rise unless you do it in oil. Pete, would you hand me that tube there, please? The PVC
Great
tube.
PVC. Oh, that one.
I'm going to show you an illustration
Of TFMS.
of tuning for maximum smoke. This is a Schedule 40 grade PVC tube, 8 inches in diameter. It was wound with 28 gauge wire that was stranded wire with black PVC insulation on it. It had approximately 600 turns. Well, that's not very many turns for a secondary coil, is it? However, the inductance ratio between the primary and the secondary was so great that what occurred was that there was a breakdown. The winding ended here and here with these little holes. And in the center, as you can see, there's nothing but air. And that was a mistake. On my larger coils, what I do is I put a lucite disc inside and divide the airspace up into 3 quadrants and then seal it with silicone. That increases the dielectric or the insulation strength inside the center of the tube, but mostly what is of concern is along the inside surface. I did not do that with this coil. Tune for maximum smoke? Indeed I did. What I'll do is I'll place this tube, and when you adjourn, you're welcome to look at it. But maybe you can see somewhat from where you are the arc trail.
Yeah.
It's carbonized and it's burned. This is a piece of junk. It's only good for show and tell. Yes, sir?
You couldn't repair that by grinding out that groove in silicon.
Yes, and I have done that. But the problem is that this is etched almost all the way through, and that's after just a single breakdown.
So it's gone through your wires on the surface.
No, it did not go on the surface. You're welcome to inspect this tube. It's not on the surface, but it's etched so deeply that I wouldn't want to trust it.
You run them hot.
Yeah, we run these coils very hot.
You didn't consider it worth saving.
I wouldn't consider it worth saving. It's not worth throwing good money after bad. And when this happens to you, buy another tube. Don't mess with this one. You're going to kick yourself in the pants when you go through the effort and you finally get the coil working right, and then the same thing happens again. It will really not make your day.
How big was the discharge off of it?
Question was, how big of a discharge was this? With 2 kilowatts of input and with a winding that was only 26 inches in length from end to end, when I redesigned this by using 20 gauge wire instead of 28 gauge wire and a much thicker insulation, so I now only have 350 turns instead of 600 turns. And otherwise, the rest of the circuit was the same, except for retuning of the amount of primary inductance to compensate.
You need a bigger toroid capacitance?
No,
also?
same toroid capacitance, still a 20-inch toroid, just like you saw in the pictures. This coil produced a 6-foot arc. But that was with 2 lucite discs inside to increase the dielectric withstand strength.
Did you use stranded wire on that, on the second winding?
Yes. Yes.
What is the advantage of the stranded wire?
The question was, what is the advantage of stranded wire? The advantage is specifically, even if the strands are not individually insulated, and if they were, that's called Litzenddraht, or Litz wire for short. That's especially good for very high frequency coils. This coil over here, which runs magnet wire, if that was redesigned to run Litzenddraht wire, especially on the secondary, you could probably get 2 or 3 times the amount of current out of it for the same amount of input power.
That's in the works.
That's the Q factor of the coil. But it is only really effective to have those individual strands insulated if you're going to run at a megahertz or higher in frequency.
Right.
You get much below 500 kilohertz, then you don't really have that much to do with having an increased cross-section. But if you run stranded wire as a bundle in a PVC jacket, that still appears as a bigger surface area than just a single cross-section of one solid conductor. So that's a good question, and that's the answer. Yes, sir.
Are you just mainly going after more of the free electrons on the outside of the wire?
It's the amount of surface area and the amount of density for skin effect. That's precisely correct. That's a very good question. Yes, sir.
I've seen a lot of pictures of Tesla's early coils, and he had a form factor of about twice the diameter of the coil was the height.
Exactly
How
right.
important is it to have those kind of dimensions?
You've touched on
other coils aren't that way.
You have touched on perhaps the second most important parameter of coil design, aside from giving proper considerations to your spark gaps. Anytime the diameter is greater than the height, then you have a form factor that is of relatively no concern. You could go 10 times the diameter as opposed to the height. And eventually you get to a form of coil which I would like to say is like this, a flat spiral. All of the turns are in just one plane. So you could go out to infinite diameter and have your high voltage in the center and your low voltage on the outside. And in fact, that's exactly what Tesla did. Pancake coils turned out to be made as very effective Tesla transformers for early power supplies for X-ray tubes. And Jim Hardesty in his paper will discuss a lot of these types of tubes and the kinds of power supplies that were driving them. Also electromedical machines, which are being sold here at the symposium, and people talk about collecting. A lot of those used pancake Tesla transformers. The primary was on the outside and there was maybe 5 turns per layer, consecutive layers, and then to the very center was a hard rubber bushing coming out, or a terminal. That was the high voltage terminal. Incredibly high Q. Way beyond critical coupling, if you've studied the phenomenon of critical coupling or loose coupling. Beyond critical coupling, you start getting double sidebands as far as your resonant rise. And what happens is that when you go way beyond critical coupling, then the whole thing is just shock excited. And it doesn't ring, it just impulse responds to shock excitation. But it becomes extremely efficient. And a lot of pulse-forming transformers are designed just exactly that way. In a coil like this, where the form factor is such where the diameter is maybe 1/5 the height, or 1/6 the height, then you start really having problems. And yet, at the same time, if you look at the patent that Tesla issued for wireless power transmission, it shows the extra coil as being very small in diameter and very tall. And that's a great curiosity. It turns out that there is no real magic rule of thumb. It depends on the application of the solenoid or the inductance, where it's placed in the circuit, and what materials are being used as to whether or not you can get away with this or not. Remember the slide that I showed you that had the 45-inch long spark off of a 20-inch winding? That had a form factor of 1 to 5. 5 inches in diameter and 20 inches, actually 24 inches in length. Okay? 24, roughly 25 inches in length. Going much beyond that, it's very difficult to control. Even if the entire voltage standing wave ratio rise is where all of the high VSWR is here and the minimum there, in other words, a quarter wavelength resonator, you still have the problem about breaking down. Because remember electrostatic fields, and remember that that principle applies here too, where if you have such an intense field and the windings are so close to each other that you invariably are going to suffer breakdown. Good question. And in the case of a coil like this, I think it's more to the design. In fact, when these guys were coming out here, how many people have seen, Science and Invention magazines? Remember back in the 60s?
Experimenter.
Science Experimenter. Anybody know who Harold P. Strand was?
I've heard of them.
Heard of him? Hey, you got a virgin audience here. Harold P. Strand was an author who did a lot of this type of work for magazine articles back in the 60s and early 70s. This is very typical of a design coil that he would make. It's very effective, it works very well. But in actuality, to answer your question, the form factor here would benefit from being a short, fat, squatty coil. Where's Mr. Beasley?
So here's a couple built. Speaking of which,
Lowell, since you're part of this entourage, you might discuss for a moment some of the form factors that you've used with some of your vacuum tube oscillator coils. Wasn't that about an 8-inch tall coil? It was about 4 inches in diameter?
Actually, it was 6 by 6. It was
Okay.
a 1-to-1 shape.
1-to-1. And how big of a corona were you producing with it?
6 inches long.
6 inches long. With what kind of driver?
With approximately maybe a kilowatt of drive.
Okay.
With a pair of, I think it was a pair of 802 tubes that I was using.
Okay.
That stretches back a ways.
Okay. Very good. Any more questions? I'm sure there are more questions. Oh, yes. Yes. Brent points out a couple of issues of popular electronics, and we'll just put these on display for you to look at how not to do things. Here is, I've never seen this before. This shows a secondary with a primary that's formed as square turns. That's sort of like trying to put a round peg into a square hole, isn't
and
it?
a disappointingly small corona.
Yes.
You should be getting 8 inches out of that coil.
The Gadgeteer's Gizmo Buyer's Guide, I believe it. Okay.
Oh, speaking, by the way, just interject this real quick. Most of you, I'm sure, have already seen this. A lot of the topics that Bill has discussed, the important parameters on effective Tesla coil design, the harmonious scaling of components, and their interrelationships, for those of you that are not as experienced in coil building, and I don't claim to be an expert by any stretch of the imagination, in the symposium, this is the commercial, book is available. It covers everything from spark gap, vacuum tube, all the way to solid state, including how a Tesla coil is used in your television set.
Yes, the proverbial flyback transformer.
So
By
it's
the way,
definitely worth checking
is
out.
there a Mr. Al Mueller in the room? No Al Mueller. Well, during the pandemonium of our friends from the fire department, someone from the front desk asked me to find out if there was an Al Mueller. Well, let's see. We're looking for Al Mueller, and we're looking for the
Didn't you
holder of the
vaporize
Discoverer
him
card.
over here?
Beg your pardon?
Didn't you vaporize him over here?
Oh,
I
maybe
was
so.
standing right over there when you hit the switch. I think maybe
Yeah.
that.
Did you ever encase any of your secondaries in oil?
The question was, have I ever encased any of my secondaries in oil? I would love to do that, and I have not. And people who have done it, and incidentally, there's some classic work that represents secondaries submersed in oil. I'm thinking of Brett and Tove, and I forget the third author's name, back in the 30s, who claimed to have produced a 5 million volt Tesla coil. Now get this, the secondary coil was a Pyrex tube, 3 inches in diameter and about 40 inches in length. And it had something like number 36 gauge wire on it with 2 copper balls on the end. And then the one primary is a pancake spiral. The whole assembly was put into a steel tank with oil, transformer oil, and pressurized to like 500 or 600 pounds PSI. Now, that's great that you could produce this voltage in this tank, but what are you going to do with it? And it was an early attempt to smash the atom. See, in those days, they were looking for power supply sources of extreme high voltage. And if you look at the evolution of the development of high voltage power supplies from static machines through induction coils, the next quantum leap was, ironically enough, Tesla and Tesla's transformer. Going beyond that, look at Mark's impulse generators, where you're charging capacitors in parallel and discharging them in series. And then things like Cockcroft-Walton generators, which is a cascade series parallel rectifier and capacitor bank. So it's like a voltage doubler or tripler or quadrupler or whatever. Those kinds of circuits are commonplace today. The pulse circuits are commonly used, and the Cockcroft-Walton circuits are commonly used even in today's power supplies. The principle is the same. But in those days, the Tesla transformer represented a hopeful, viable alternative, since the Van de Graaff generators and so forth, the other static machines, were not producing a high enough potential at a high enough current. And this article deals with trying to take a Tesla coil submerged in oil and generate a high enough voltage. They were somehow going to extract that power out of that pressure tank and use it to try and accelerate electrons to the point of smashing some atoms or something of that nature. It didn't work, needless to say. And the treatise on the design and the theory of operation of that circuit is very interesting, because they used a rectifier to first of all rectify the AC to DC before sending it to the primary oscillatory tank circuit. And interestingly enough, Tesla also did this at Wardenclyffe. It is believed that he did this, that he had several modes of excitation of that equipment. But if you stop and think about it, if you've got a good tuned circuit, capacitor, primary, secondary, and you're trying to tune for maximum smoke, what are you going to do? You're going to put in more power, hit it with a bigger hammer, right? The next thing that you're going to try and do is try and make this guy like a continuous wave oscillator, so that its amplitude is constant and continuous. That's what you're getting over here as CW. But the way that you get it is with these triode oscillator tubes run in an oscillatory fashion. That's fine, but how much power is being delivered there? A couple of watts. How much power can be delivered here, even though it's not continuous? It's just oscillatory pulse wave trains. Hundreds of watts, thousands of watts. The sky's the limit based on design. So a spark gap driven Tesla coil is, to me, the only true Tesla coil. Everything else is a variation on a true Tesla coil, much as is the flyback transformer in all of your monitors and TV sets. Well, it turns out that if you had a DC source in a spark gap driven Tesla coil, and if you had a capacitor that could charge in an infinitesimally short period of time, and also discharge that energy in a very short period of time. And then on top of that, if you also had a spark gap or a switch that would turn on and off any number of times per second or per unit of time that you wanted, then with what I call like a infinite battery, because that would be like a DC source of infinite current reserve at a fixed voltage rate, you could get an incredible amount of power out of this. And Dr. James Coram treated that in a number of his papers discussing an analysis of Tesla's magnifying transmitter. If you look at all of these accelerators that have been built with the